Sweet. So this question is about, think about a board game where each step on the board basically represents how many squares you can take. So, for example, given this array or this board, if you're right here, the most steps you could take from this spot would be 1, 2, 3. So all these are all visitable. Same for this one, 3, 1, 2, 3. You could visit this node. And basically we're trying to, the goal is to write an algorithm that says given an array, can we reach the end based on the rule I just said. In this case, you would be able to. The steps would be to jump here, 1, 2, to jump here, and then 1, 2. Because we reached the end, we would return true. A counter example would be 3, 2, 1, 0, 5. Because if you look at all these, the max 3 can travel to is here. Same with 2, same with 1. So no matter what, we get held up at here. So that would be false. So there's several ways of doing this. One way is you could say, okay, here's our array. 1, 0, 2, 0, 1. You could say, hey, why not just keep an auxiliary array of whether we can visit, whether something has been visited or not. Visited. True being it has been visited, false being it hasn't been visited. I'll just keep it blank for now, but for this example, you could go through and you say, okay, 3. The first one's always visitable, and then you would say, okay, the next 3. Okay, and then you'd go to the next one. You say, okay, 1, 2, 3. And then this one, you'd mark this as true. 0, you wouldn't do anything, and you'd go through the entire thing and eventually mark it as true. We're using an extra array, so that would be O of n space. And then we're potentially going, if we don't think about quickly exiting, we're potentially going through this n squared times. So maybe it didn't seem like that in this example, but if these were bigger numbers, we would have searched everything from here, everything from here, everything from here, potentially, worst case. Let's do better. So one thing we could do would be to say, okay, why do we even use that auxiliary array? Why not just try everything and see how far we can jump? So for this, we would say, okay, the max we can go is this 0. So this is our search space. And that implies that all of these are visitable. And then we would say, then we would go to this next 3 and we say, okay, 1, 2, 3, that would imply all of these are visitable. And we'd keep going down until we eventually realized, okay, all these are visitable. That's the same algorithm, but in place. So in constant space, so it's better. But let's work on fixing the actual searching. So here's our original array again. Say we kept track of a value that basically said, okay, this index is the furthest we've been able to reach so far. I'll call it farthest. start off as 0. And we just continually updated that. So in our first iteration, okay, what's the furthest we could reach so far? Well, it's the biggest of this value, which is 0, and this index is 0. I'll write the indexes up here. Plus the value. So the farthest would actually be index 3. And then we'd go through again. We'd say, okay, what about here? What is the furthest we can reach? And it would be 1 plus 3. So 4 or 3, whichever one's bigger, it would be 4. And again, our search space would now increase from 0 to 4, or not our search space, but like the places we could check. Okay. Where were we? Okay, so we know this is the space we're looking at right now, and the farthest we can reach is 4. So let's examine this. Okay, the furthest we can reach is this one. So 2 plus 1, which is equal to 3, which is actually less than 4, so we won't update that. Now we're looking at this value, 0. Is 0 plus 3 greater than 4? No. Is 4 plus 2 greater than 4? Yes, 6. And at any point, if we know that we can reach this spot, we should quickly exit. And yeah. So let's see what that looks like in code. Okay, so given an array, see if it's possible to hit the last index. We needed that value the furthest. And that will be 0. And then we're going to go through each of these items, but we're not. So we can't just do a simple for loop to say, okay, we're going to hit each one of these items because it's possible it's not, we can't reach them all. So it will have to start off as, it'll basically have to shift. At first it was this, and then it was these 3, and then it was these items, and then it was all of them, updated by this. So we'll get to that in a sec, but furthest has to update at every single point. And like we said earlier, it has to be the biggest of whatever furthest currently is, or this value plus this value. So that would be the index we're currently at, plus the value there. So max advanced steps I get at I. And then we'll see at the end, we just have to return if this furthest value we hit is this value or greater, because we may have skipped way past, but that's still valid. So we return furthest is greater than or equal to max advanced steps dot size minus 1. That just means it's either on this index or greater than that. Let's write this for loop. So we're going to start at 0. That part's easy. What are our conditions? So essentially, the space, I is where I drew the arrows here. It's where we can currently visit, and it seems to be capped by our furthest so far value, because at first it was 0, and then it was 3, 4, 6. So let's write that in. So I is less than, and it will be or equal to furthest, because otherwise it wouldn't run the first iteration. And then we'll also run into an issue here, but I'll get to that. So if I is, let's see here. we might run into an issue where basically we need to shield this get call. So if at any point in time I is less than max advanced steps dot size, that's just making sure we won't get a index out of bounds exception right here. So let's run through what we're actually doing. Furthest equals 0. Furthest at this first point, it passes the conditions right here. Furthest on this first iteration will be index 3. I will be 1. I is less than furthest, yes, and it's less than the size. The furthest will be 4, because 4 is 1 index, or 1 right here, and then the value there, 4 is greater than 3. We'll continue and basically continue increasing the size until we get to the end. Let's run our test. So we pass all our test. Average running time 11 microseconds. One way you could optimize this if your interviewer asked would be to quickly exit if you ever hit a point where furthest is greater. Basically, if you've already, you don't need to test every single value if you've already hit the end. So in a case where like you had 52 and then 50 zeros, in that very first iteration, you would know that hey, the furthest is 52. So at any point we can say if furthest is greater than or equal to size minus 1, we'll just return true. It makes the code less clean, but it does run faster. Not according to this because it takes so little time, but that would be an optimization.